Okay, so I finally got everything typed up. It took forever, um, but I finally got it done. I could have just sent this to you, but there's a lot of nonsense and questions that I posed to wade through, so I figured I'll just kind of like work through the main proofs and the main ideas in this new section that I added to my paper. Um, and I will also go through one calculation because there's one calculation that's kind of um not immediately clear, and I might have to like rework the calculation, but hopefully it will make sense. So let me share my screen. All right, so hopefully you can see what I'm seeing. So I added this. Yeah, now this paper is now like 60 pages or something like that. So yes, 60 pages. I'm it's gonna be smaller because I'm gonna cut some stuff out. So it'll probably be about the same, but I have this new section. Where is it? That I added. Um, yeah, so I had to, as I said, I had to rework the paper a little bit. Um, so cut a little bit out. And I've kind of treated these properties, the weak asymptotic homomorphism property and irreducibility, sort of as distinct properties. I didn't realize that they were the same. So yeah, for here, right here, I said, this is where this is the end of the section where I construct an example. So, right here is the end of a section where I construct an example where you have irreducibility and the WAP. But that's if you have the WAP, it's already, if you already have an example where you have the WAP, it's going to automatically be irreducible, and the calculation is pretty trivial. So I got to kind of reword things a little bit, cut things out a little bit. So nothing fundamentally changes. There's nothing fundamentally changes. There's nothing incorrect about what I've written, but I got to do that. And so once I do that, and once I this new section I've added, once I've kind of like got that in its final draft, I will send you this um paper, and maybe you could take a look at it, quick look at it before I send it back to the journal with Andreas Tom. So let's look at this section. And as I said, there's a lot of nonsense I wrote here. I gotta like clean this up a bit. But basically, in this new section, we're going to look at inclusions of Thompson-like groups. So, and throughout this whole paper, we've studied this inclusion right here. Let me highlight this. LFD inside these Thompson-like groups. Um, and basically the main idea is that if you have this cloning system equipped with a diverse cloning, if the cloning system on a sequence of groups is diverse, then that's going to imply that the inclusion, the highlighted inclusion right here, is irreducible. And so it being irreducible, I'm sorry, it's going to satisfy the WAP. And it satisfying the WAP is going to imply irreducibility. It's going to apply singularity. It's going to apply that's quasi, that the quasi normalizer is trivial, quote unquote trivial, in the sense that um all the quasi normalizers come from LFD. And so it's going to have a lot of consequences. And so this diverse property is very, very strong. So now the question I pose in this paper, and the one I've been thinking about, and it's actually kind of good that I've realized that WAP implies irreducible for its own sake, but it really caused me to go back to work through this paper and start thinking about that question of whether or not I can construct a singular inclusion of an infinite index singular inclusion of two n factors, which does not satisfy the WAP. And I was actually able to answer that now. So that kind of like ties up a loose end in this paper, which is nice. Um, and there's some other loose ends that got tied up because another thing I was trying to think about is whether or not you can have whether this highlighted inclusion can be irreducible but not satisfy the WAP, and that's before I realized that one WAP implies irreducible. So I can remove that as an open question as well. So this is actually good. It's going to make the paper more self-contained, no loose ends, and now that we have this new section, I think the paper will be a lot better, even a lot better. Um, So let's kind of work through the idea. So what's the idea? So this we're going to primarily in this section look at the modified direct product examples. And for that, the cloning system is always diverse. So what that means is that this inclusion for these modified direct product examples, it will always be satisfy the WAP. So that's one problem. So although this inclusion is always going to be infinite index, aside from some trivial cases, it's for the examples we look at, it's never going to satisfy. You're never going to be able to get singular but not WAP for this highlighted thing I highlighted. Um, so we have to be so the constructions actually be pretty delicate actually. We don't want to just look at the direct product example. We want to look at the modified direct product example where you have one in the first entry of the tuple. And so this it's going to be actually a pretty delicate construction. So basically the idea is we're going to Thompsonify inclusion. Um, so this is one example of an inclusion of Thompson-like groups. But we can use cloning systems to get inclusions of generalized Thompson groups. So basically the idea is you take an inclusion right here, just take any group inclusion, and then you're going to Thompsonify it by passing it through the modified direct product d-ary cloning system. The size, those psi groups. Um, so this is what we're gonna do, and this is actually a really cool topic, I think, in general, to to construct all the different ways you can Thompsonify an inclusion. So, for example, like you have this functor right here. You send G to the this is the modified direct product example. There's this is just the regular direct product example. So these are, you can pass this group inclusion right here, to get an inclusion of there's TD psi star of them. So like basically, let me see if I can write, so annotate. So if you have like, this inclusion right here, you can pass it through these to get this inclusion right here. Um, So this is going to be like one way to Thompsonify an inclusion. You can also use this functor. This one might not be as useful, but what I would like to do, and this is just, I have independent interest, is to come up with a V-like machine of this. So for this one, this is really nice because you can plug in any group. Remember, these direct product examples come together with monomorphisms. We generally think of the monomorphisms as just all being the identity, and that's what we're going to actually do in this section. But this cloning system is diverse for any choice of monomorphisms. And then what that means is that this will be a 2-1 factor. This inclusion right here will satisfy the WAP. It'll be singular, irreducible, etc. No matter what you choose your monomorphisms in group to be. Now, if you further assume that the monomorphisms are the identity, then this guy right here is actually also a McDuff factor. So these are really awesome examples. And they're going to be they're going to also be useful to construct an example where you have singular but not WAP. So my one thing I'd like to do, so we have this way of Thompsonifying an inclusion, this way of Thompsonifying an inclusion. I would like to get a V-like machine that's like this one right here, where you can plug in any group and you'll get a V-like group. Notice, remember, these groups right here give you F-like groups. They give you F-like groups. But I want a machine that gives you V-like groups. Remember, what it means to be V-like is that your representation maps from Gn to Sn are surjective. This will give you, of course, in the case of this one and the modified and the regular direct product example, the representation maps are trivial. So we would need to come up with some sort of machine where the representation maps are all surjective, and it's kind of like the direct product example. There is an example where you do like G wreath product Sn, and then your representation maps are from here to here to Sn is just like forget this factor. And then you'll get like TDG star will be something like G wreath product S star. And this is good. This will be like this actually is a V-like machine. The problem though is that it has the same shortcoming this one does right here, where the only way to ensure that this is a factor or it gives its ICC is if you assume the monomorphisms, their images intersect at the identity. And that's kind of an annoying restriction. Like for this example right here, we don't have that restriction. You can just choose any monomorphisms, and you will get a factor. You get irreducibility, WAP, singularity, everything. So it would be cool if we could come up with some V-like machine that's like this. So we need to like modify this construction right here. I'm not exactly sure how to do that. But if we could come up with a V-like machine like that, then that'd be like a third way to Thompsonify inclusion. So you can get like you can Thompsonify inclusion, this inclusion right here, and get F-like groups, and then you can get V-like groups, and you could probably even do it to get T-like groups. So for now, we're just gonna think like about Thompsonifying groups in this way right here, or some variation of that. So let me. I don't know if there's a way of clearing the screen. I guess it is all the drawings. All right. So let's look at what we're gonna do in this section. Wait, I need to get rid of the pen as well. I guess I just click this right here. All right. Okay. All right. So let's see. Yeah. So although this is always um, all right. This is always infinite index, as I said, aside for some trivial cases. It's not going to work because in all the cases where we are going to look, the cloning system is diverse, so this will always satisfy the weak asymptotic homomorphism property. Remember, we want a singular but not WAP. That's the kind of the goal of this section. We're looking at inclusions of Thompson-like groups that we're going to give a singular but not WAP. So here's kind of the first lemma. This is actually cool. Like this is a lemma I proved a long time ago, and I wasn't really thinking about using this to get a singular but not WAP. I was using it because I could prove this nice index formula right here. Um, and I was like, oh, this is cool because then I can get inclusion of von Neumann algebras for every integer index. But then I was like, I don't know if that's really even interesting. So I was like, yeah, I'll just scrap this for now. But now it ends up being useful. So this is really awesome that I can actually use an old result. So what does this say? So we're going to look at inclusion of groups H and G. We're going to find Gn to be our psi n of G. This is going to be our like modified direct product example. And we're going to just take these guys to be the identity. Now, so this is our Gn. Now you might think, all right, okay, well, Hn should then be whoops. Maybe we should take Hn to be psi n of Hn. And I think this will work, but the calculations get really, really difficult, actually. I'm going to think about this more. And in fact, things might break down for the WAP if you try to define it this way. So instead, we're going to define Hn to be, again, you want the first entry to be 0, and that's going to be G cross G cross G. And then the last thing is going to be H. So when you do that, you're going to get this nice index formula. If you instead define Hn to be this, it's not clear what this index is going to be. It's actually kind of hard. It's definitely not going to be equal to this. It might be greater than or equal to this, which is fine, because then if we assume that this index is infinite, then this index will be infinite. But I don't know how to calculate this index when you take Hn to be this. This is a good, in other words, I don't know how to deal with this inclusion right here yet. I don't know, it's gonna look horrible. This inside of this. This is a good inclusion to study. I don't think you're gonna get a tight formula like this. It might be something weird like G index of G and H and G to like maybe like D minus one power or something weird. I'm not sure. I don't know how to get it. I mean, it might be that you can get that it's greater than equal to, which would be cool. That's all you need. I'll think about this, but it ends up being real. The calculations work out a lot more easily in some cases. Some cases they're the same, the calculations, but in a lot of cases the calculations are easier if you look at if you take HN to be this. But this might be an interesting inclusion to study in general, maybe later. Um, so yeah, so this inclusion is definitely not really ever going to work, I don't think. To get us whoops, to get us um singular but not WAP because in basically all the nice examples this thing is diverse and hence satisfies the WAP. So this is going to be it's going to be very super careful, but we're going to need that this is irreducible, which the WAP implies. So it's yeah, I won't. You'll see. It's going to be a very careful construction. I'm really happy with this example that I construct. All right, so let's clear this again and work through the proof. All right, um, or well, let me read the statement. You probably read this while I was rambling, but let me read through it. So yeah, you have inclusion of groups. I didn't actually finish reading the whole statement. And then Gn is equal to psi n of G, phi or identity, and then you're going to consider these subgroups Hn, which are the Hn is going to be a subgroup of Gn. It's basically like almost like psi n of G, except the last factor has to be H, which is important. That's how we're gonna like get this formula right here. So the usual d-ary cloning system on these modified direct product examples restricts to the d-ary cloning system on this. And just to remind you, what are the cloning maps on the direct product example, just because you don't remember. So let me annotate. So the cloning map or just more generally the direct product example. You don't necessarily need the first entry to be the identity. So kappa kn. So of course the representation maps are trivial. But what are the cloning maps? So kappa kn on this tuple, basically you look at the kth entry. And in this case, we're taking the identity these to be the identity. So it's usually it'd be like at the kth spot you replace gk. So there'll be like a gk in here somewhere, and you'll replace the gk by this block of length d, and it'll be phi1 of gk, phi2 of gk. But in this case, they're all the identity, so it'll just be a block of gks. Another gk, gk, and then gk plus one. So kind of like it replaces the single GK in these ellipses with this block of GKs, and then it goes all the way down to GN. So that's how these cloning maps work, just to remind you. All right, so these are pure cloning systems. So first note, this is the index of the von Neumann algebras. It's just going to be the index of the inclusion of the groups. Oh, I still didn't finish reading this. All right, so so the usual d-ary cloning system on this restricts to this. And then actually this d-ary cloning system is pure, uniform, and diverse. So this inclusion, what we'll be able to see is that this inclusion is irreducible. In fact, these are type 2 unfactors, which I think is kind of besides the point. But so I'll take that out, but I'll like make that a remark at the end of the lemma. Like, oh, notice that these are also 2 unfactors, which is kind of are. I mean, they're obviously going to be obviously be 2 unfactors, but they're also mixed up, which is pretty cool. All right, so this is the main part of the lemma though, because I need that to prove that this index is going to be infinite. That's what we want. We want this index to be infinite. And so as soon as your group index's inclusion is infinite, their von Neumann algebras will be infinite. Inclusion will be infinite as well. So first note that this inclusion right here of the von Neumann algebras is just the inclusion of the groups, or the index of the inclusion of the groups. And now the cloning system's pure, so this group right here, this group's splits as this semi-direct product. And then this group right here, that splits as this semi-direct product right here with the H's. And then it's just kind of a general fact that if you like have this inclusion of these groups, and then the acting group is the same, then you can just cancel that out and get this. And this is actually a group because this thing right here is normal inside of this piece right here. All right. And I know that this index formula right here holds just more generally for any pure cloning system on a sequence of groups such that when you restrict the cloning system to this sequence of subgroups, the cloning system respects it. And so yeah, the fact that this cloning system restricts is trivial calculation, and then the fact that the d-ary cloning system restricted to the sequence of subgroups is pure, is uniform, and diverse just follows from the definitions. So yeah, so that's yeah, these are just trivial observations really. And then we have, yeah, then the 2-1 factors, who cares about that? All right, so here's the main part. Let's prove that these that the index is equal to GH. So I typed this up fast, so there's some typos. So based on this right here, to prove that this index is equal to the index of H and G, it suffices to show that this index is equal to the index of this one right here. Okay. So how are we going to do this? Well, what we're going to do is we're going to take S, some subset of G, and this is going to be a set of distinct left coset representatives. Maybe I should just, instead of highlighting this, let me use the pen. I don't know if that makes it easier. All right, so we're going to take S to be this distinct set of coset representatives of H and G. Of course, that means that the cardinality of S just is the index. And here's the claim to get the formula that we want, is that we claim that these elements right here, where X is an S, and of course, since like you have 1, 1, 1, 1, 1, 1, and then X in the last entry right here, this is just this is the only thing that can vary, and X is in here. There are going to be the number of elements of this form is just going to be the index of H and G, or the cardinality of S. So yeah, this is also this right here, lambda D is going to be the d-ary caret. So this is a tuple of length D, so they're going to be D minus 1 ones, and then the last entry is going to be X. And X is an S, and so the number of elements of this form is this right here. All right, so now first of all, I guess I didn't type this in. It's pretty clear that these are pairwise distinct. You don't have to worry about, like, if you set two of these equal to each other, the trees are going to be the same. In fact, it's just the d-ary caret. So if you set these two equivalence classes equal to each other, so you have like, suppose you say this equals something like this. We're not letting the trees vary, so you can literally just set these tuples equal to each other, and then that would imply X equals Y. So these are truly pairwise distinct. And then we want to show that if I take any element that represents some arbitrary element in this quotient, I want to show it can be written, it reduces to something of this form in the quotient. All right, so we have like two equivalence relations going on. We have the equivalence relations from these triples, which give you the group elements in Thompson's group, and then we have this equivalence relation and that gives rise to this quotient group right here. And we're actually, what we're going to do, we're kind of going to do in the course of this proof is show that these two equivalence relations, the Thompson group equivalence relation and then the quotient group equivalence relation, they kind of commute in a sense. They're compatible, which is kind of cool. All right, so let's see. So how do I do this? So yeah, we take an arbitrary element and we're going to say let it represent something in here. And then so we have some d-ary tree T and then some group elements. And we're going to argue that it's equivalent to some element of the form star. Ignore this right here. And up, we want to show it's equivalent up to expansion and modulo the group that is the equivalence relation you get from the quotient group. All right, so given G in here, we can find some left coset representative X and S and some H and H such that Gn is equal to XH. And then now we're going to take our triple right here. We're going to, I actually didn't completely write this out. I'm going to take Gn and replace it by Xn. And then I can take this and split it off as a product like this. So I have my tuple right here, and then this right here. Now, we're thinking about elements in the quotient group. I'm like not using that quotient group notation. Like really, there should be like a KD, H star here to denote the left coset. But I just feel like that's just awkward notation. So we're working on the quotients. Now we want to take this thing and we want to mod out by the equivalence relation. But notice this element right here lives in KD H star, right? Because you have this is in G, this is G, but the last entry right there is in H, right? And that's true no matter what sort of expansions you do on this triple. And that's kind of due to the fact that we're taking the identity, all the monomorphisms to be the identity. Because no matter where you clone, if you clone at G2 or this one or even H, you'll just get copies of those elements. And always that, no matter like even if you clone this last H a million times, the last entry will be H. It won't be something like phi d of H, which that's a problem if this phi d of H is not the identity, this could push you possibly outside of H. So it's important that these monomorphisms are the identity. If maybe if you assume that the monomorphisms map H into H, that's not a problem, which is cool because I actually talk about this at the end. If you take H to be a normal subgroup and then take these to be like inner automorphisms or something like that, or just automorphisms with which fix H, you get some cool examples, but that's besides the point. Anyways, so what are we trying to do here? So we took this element, which is supposed to represent just some coset in the quotient group. We split it as this product right here. Now the second factor is in here. So when you mod out this thing, this element right here is equivalent to this. So you like kill the second part in the second factor. It's equivalent to that in this quotient. So we've already used the one quotient equivalence relation for sorry, we used the one equivalence relationship from the quotient group structure. Now we want to argue that this is equivalent to this, an element of this form, using the Thompson group equivalence relationship. All right, so let me clear the screen and scroll down a bit. All right, so now what are we doing here? So we want to basically show that if I take something like this shouldn't be an xi right here. It should just be an x. So that's another error. If I take this right here and I do some expansions on it, I can get to something like of this form right here. Yes, and there'll be a little challenge in the future when we go on to the next page, but it'll be fine. So what do I say here? So since any d-ary tree can be inductively, oh, let me go back to using my pen. All right, so any d-ary tree can be, so if I start with the caret, I can just add carets all over the place so that up to expansion, these guys are the same. I can just add, if I start with the fundamental d-ary caret, I can just add carets all over the place and build up the caret to get this right here. So if I start with this right here, again, there shouldn't be an I here. These should be they shouldn't be there. I can apply the appropriate sequence of expansions and then apply the appropriate sequence of cloning maps to this guy. Now I don't really have control because I don't know what T looks like. It's possible that I could have to add carets to the last leaf. Now, if I do that, if I do that, when I expand this to get to this right here, if I do that, if I have in in the process of building up the caret to get T, I have to add carets at the last leaf. It's possible that I could clone this last coordinate. So there's a possibility I could have a block of X's here. Again, no I's. I don't want to use the I notation. So it's possible I could get this block of X's if I have to add carets at the last leaf in the process of building up this thing right here to get the T right here. And that's fine. So now this element doesn't look exactly like this one right here, but I can split things off if I need to, and then use the quotient group structure again to cancel those out. All right, so now again, so we have this right here, we have this underlined block right here of X's. Now the underlined block might be empty depending upon whether we need to clone the last coordinate at any point in expanding lambda d to obtain T. Now, if the block is empty, as we never had to add a caret to the last leaf, we're done. This block won't be there. It'll just be actually a block of ones, and it will equal this thing right here. So in other words, we took this guy right here, we split it off like this on the second line to get this, and then we could expand one of these elements right here to get to this. So in other words, in the quotient, this element right here reduces to one of these elements. So it's like it will represent that. In other words, like this can represent the element. Now, if this block is not empty, that is, you had to clone the last coordinate. You had to add a caret at the last leaf in the process of expanding lambda t to obtain T. That's not going to be a problem either. However, if the block is not empty, then we can take our element and we can split off the block here, and then we'll end up with this thing, and that is the element we want. And then of course now so again, we're working in this quotient still, so we can mod out. And when you do that, this factor right here cancels. Actually, maybe I should have wrote this on the other side. Yeah, I should, because they commute these two. Yeah, I will fix that. I'm gonna there's a lot. As you can see, there's a lot of stuff I gotta fix. The notations are off. I should actually write this on the other side. I should switch them, which is fine because, as I said, they commute. In any case, when we're working as a quotient, this factor right here cancels out because this factor right here lives in this group right here, so it gets killed. Because it's a subgroup. One is definitely in H. And so in any case, what we've shown, so now we can, like, doing multiple reductions, modding out possibly multiple times, that element we started with reduces down to this, because this thing right here survives the quotient. Possibly, maybe. Well, no, yeah, it will definitely, in most cases, survive the quotient because X right here is probably not going to be the identity. Um, and so it's not going to ever represent the a trivial coset, I guess. So now what we've shown is that in any case, using expansions and reduction modulo of this, we've shown that any element in here in the quotient um, is a equivalent to an element represented by something of this form. Again, there's no I there, and then X is in S because S is this distinct set of left coset representatives. This is when I was dealing with finite. The index is finite. Anyways, what this shows is though is that that basically proves the formula because the number of these things is equal to the index of H in G. So that gives us the formula. I'm gonna actually pause for a moment. Use the restroom. Okay, so sorry about that. Let me share my screen again. All right, so that proves the lemma. So let me just scroll up so we can remind ourselves of what it said. Said a lot. There's like a lot that I can just remove, but it says you start with inclusion of groups. You define Gn to be psi n of G, phi are all the identity, and then you define Hn to be this. You don't define Hn to be psi n of H, but you want it to be a little bit different. You don't want this to be like 1 cross H cross H cross H cross H. You want it to be G right here cross itself a bunch of times, and then the last thing you want is to cross it with H. You want the last thing in the tuple to be something in H. Then yeah, you get that these are McDuff factors, etc. But importantly, you get this. You can completely describe this index in terms of G and H. H in G. So let's see. I will send this to you anyway, so you can read through it. Like you can obviously skip all the stuff I skipped right here because this has got to be cleaned up. But you can read through Lemma 4.1 if you want to like work at it on your own and carefully, I guess. And then there's Lemma 4.2, and then there's going to be Lemma 4.3 we're going to work through. And then there's finally the construction of the inclusion, which is singular but doesn't satisfy the WAP. All right, so let's read through, where is it? 4.2. So now this one's going to be the easier thing to prove. So now we have an inclusion of groups H and G. And then so we're still taking, and we're going to, sorry, let me get my pen. We're going to take G. We're still using the same setup. G is going to be this. Gn is going to be this, and then Hn is going to be 1 cross G cross self G, and then in the last spot it's going to be H. We're going to use the same setup. So now, if you have that setup and you know that the normalizer of H and G is trivial, that is to say, H is self-normalizing in G, then the normalizer of this group right here is and here is trivial. That is, this group right here is self-normalizing in here. So this is not terribly difficult, this calculation. So this right here actually works if you instead define if you define Hn to be like this full group here, psi n of H. This Hn is going to be, or I should say, this thing right here is oh no, wait, this is a subgroup of that. Anyways, this lemma right here works even if you take Hn to be this. Things might break down in lemma 4.3 if you try to define Hn this way. And again, there's also the problem of I don't know how to describe the index in this case. But I just want to point that out. All right, so how does the proof work? So we're going to take an arbitrary element in here, which normalizes this subgroup, and we want to show that it actually lives in here. So T and U are going to be some d-ary trees, and then G1 through G and G2 through Gn are in here. And as I said, we want to argue that that element lies in here. And so to do that, we're going to argue that Gn is actually this thing right here in the last entry. Gn is actually a normalizer of H inside of G. And of course, by assumption, the normalizer is trivial. So here's how we do that. Just take this element right here. And then it's definitely going to be inside TD H star because we're going to take H to be just arbitrary. And then so now we're going to take this element right here, copy it down right here, and we're going to conjugate it by this element. And we know that this has to live inside of the subgroup TD H star because this guy right here is a normalizer of it. So what's going on here actually? Is this just continue on the next page? Uh-oh. Oh no, wait, it's just one calculation. It's really trivial. It's not it only needs one line. So sorry. Why isn't this working now? There we go. So yeah, when you invert this, you just invert each group element like that. You pass the inverse through. And then when you invert this, you swap the U and the T. That's how inversion works in these Thompson groups. And then actually these should not be T's, they should be U's. But it doesn't really matter. All that matters is that when you multiply these, you multiply the tuples through. And actually, this should not be even here. There should be no G2. It should be identity because this G2 is going to cancel. This G2 inverse is going to cancel with this G2. So it's just going to basically be a bunch of ones. And in the last entry, you're going to have Gn inverse H Gn. And so by assumption, this belongs to that because we assume that the conjugating element, the element we're conjugating by is a normalizer. So that means that this guy lies in here and H is arbitrary. So that means when you conjugate in this way, it sends H to H. And that's because H is arbitrary. Now it just reverse the roles so you reverse the roles of this factor with this factor, just swap them around. And that will still normalize it because if a group element normalizes it, the inverse also normalizes it as a subgroup. You can show well, I forgot to put the subset there, I guess. You can show that G and H G inverse now. So these things will swap is like that. So you have that Gn inverse HGN maps it to H, and then the opposite thing holds. So it's just a normalizing element. So the Gn lives in the normalizer, but we assume that to be trivial. So yeah, we didn't even really need to assume that H, yeah. Anyways, I won't say that. Sorry if this is like, it sounds like I'm rambling and stumbling a lot. I literally just finished typing this up, so I wanted to get this out as fast as I could, so I can get this video out as fast. Yes, get this video out as fast as I can. So that's the lemma. Basically, it states that if you start with this an inclusion which has trivial normalizer, and then you Thompsonify the inclusion, the Thompsonification will also have trivial normalizer as well, and that's good. Now this is the cool part, and you'll see it later on. The example we're gonna look at is the infinite dihedral group. This inclusion will never be irreducible, but when you Thompsonify it, it will become irreducible, and then that together with singularity means that the von Neumann algebra normalizer has to be trivial, because when you have an irreducible inclusion of group von Neumann algebras, that von Neumann algebra normalizer can be directly computed in terms of the group normalizer by result of Smith and Wiggins. So like I said, this is a really delicate construction because we're going to start with a group inclusion which is not irreducible, but when you Thompsonify it, it will become irreducible, and then that will allow you to easily compute the von Neumann algebra normalizer. All right, so the last one, the last thing is limit 4.3. So again, you start with inclusion of groups, H and G. Now, what we're going to say is if this does not satisfy the coset covering property, then the Thompsonification, the inclusion does not satisfy the coset covering property, then the Thompsonification does not either. What is that? So let me scroll all the way up here to find out, to show you what I mean. So irreducible. All right, so we have, here's the weak asymptotic homomorphism property. It has this reformulation due to Smith and Fong and some other guy. That the weak asymptotic homomorphism property can be described in terms of these one-sided quasi-normalizers. Now, this is the general von Neumann algebra case, but when you look at this right here, this condition right here, when you switch to group von Neumann algebra case, this condition 2 becomes a condition about covering cosets right here. This is due to Fong, Smith, and some other guy. So what we have is that this inclusion right here satisfies the weak asymptotic homomorphism property if and only if 2 holds. That is, whenever you have these group elements in here, where this right coset can be covered by these left cosets. I can't get it right here. These left cosets, then necessarily that group element coming from this right coset has to belong to the subgroup. So this right here, property 2 here is what I call the right coset covering property. I don't know. I don't think I just kind of came up with it myself. Maybe it's not good terminology, but that's what I mean by right coset covering property. So in other words, if you don't satisfy the right coset covering property, that's equivalent to this inclusion right here not satisfying the WAP. So let's go back all the way down to back here. So what we're saying in this theorem right here, 4.3, is that if this inclusion does not satisfy the coset covering property, that is, the inclusion does not satisfy the WAP, that is their von Neumann algebras, then this inclusion does not satisfy the WAP either. And that's important. All right. So suppose this does not satisfy the coset covering property. That means that there exists a group element G that's not in H, and then these group elements Y1 through YT in H, such that this right coset can be covered by these left cosets, even though G is not in H, because we're assuming it doesn't satisfy the coset covering property. So now, sorry, we're going to take, so we want to show now that this inclusion does not satisfy the coset covering property. So we're going to define this element X. This is a mistake right here, sort of. This X right here should actually be capital lambda D sub D, and then a bunch of ones, and then G, and then capital lambda of G. So this is going to be an element of TDG star, which does not belong to TDH star, because this G right here does not belong to H. And now we're going to define Xi to be this. Again, these should be capital lambdas. And then we're going to take it to be Yi. And the claim is that this right coset is covered by these. And if we can do that, we're done, because this X right here doesn't belong to this subgroup. All right, so now we're going to take an arbitrary element of that. So we need to take an element of TDH star. So this is going to be this arbitrary element here. And then this will be for some d-ary trees T and U, and then some H. This H right here belongs to the subgroup H. Now, HG is in here, which is covered by these cosets. So there exists an I between 1 and T and some H prime, such that HG is equal to YI H prime. So they swap in this way. Now, this is where it gets really, really complicated. So I'm going to I'll run through this calculation and I'll kind of explain. I might try to figure out how to use better notation, but I will run through it and then maybe do an exam. I will definitely do an example calculation to kind of illustrate what's going on. Okay. All right. So now we want to show that this right here lies in one of these left cosets right here. So what we're going to do is we have lambda d. This is the caret. So the fundamental d-ary caret. So you would just add leaves wherever you need to, and to build lambda d up to equal u. So that's what's happening here. So we go from lambda d to u. Now, again, we're going to have this underlined portion right here, which could possibly be empty. But we always have in the last coordinate g. So this is if in the process of building lambda d, like adding carets to obtain u, we have to add a caret at the last leaf. We have to clone this last coordinate right here, and it will introduce a block of g's every time we do that. Every time that we have to do that. Now, so now these trees right here equal, so we can multiply. Sorry, these trees agree, so we can multiply these two tuples, and what we'll get is t and then u, and then in this middle, what we have is epsilon here, epsilon. So it's g times epsilon 2, g3 times epsilon 3, all the way up to gn minus 1 times epsilon n minus 1, and then finally times h times g. Where the epsilon I is going to be either 1 or g, depending upon whether this block is empty. So if it's empty, this will just there won't be if this block right here is empty, all these epsilons will go away. It'll just be g1, g2, g3 all the way up to gn minus 1. But if it's not empty, then this will be g2 times g, this will be g3 times g, this will be gn minus 1 times g. So that's why you have to throw this epsilon in there, depending upon whether or not that block is empty or not. All right, so now what we want to do, so let me get rid of some of this now. So now we have h times g, but h times g is equal to y1 times h prime. All right, so now that explains this line. Now these we had to write on. It was running off the screen, so I had to write this product on 2 lines. So now what we're gonna do is we're gonna split this thing right here as a product. How are we gonna do this? Well, first of all, why? Oh, this is really messy. Now I'm confusing my. Oh, all right. This is gonna be really awful. I need this block right here possibly is empty. It might or might not be empty. But what I need to do is I want to show this element right here is equivalent to this right here. Now again, if up here I had to clone at the last spot, this block will not be empty. And if I had to clone at the last spot, then when I take this tuple right here and I reduce it to this, I might have to remove things at the last spot, the last leaf. So what I need to do is in this factor, I need to introduce delta 2, delta 3 up to delta n minus 1, where delta j is either 1 or yi inverse. And then those yi's will cancel this block right here. So I didn't really change anything, but I need to throw those in just in case when I let's see when I remove carets from T to get down to the fundamental caret, it's possible that I have to remove things at the last coordinate, and so I have to remove blocks. of yi's. Okay. So now this all happens. You have all these blocks right here, you have this block right here, and you have these epsilons and deltas, depending upon whether we need to clone the last coordinate in expanding the triples to obtain t and u from this fundamental caret. So as in the proof of the above lemma, these underlined portions could possibly be empty if we never need to clone the last coordinates in the process of building t and u from lambda d via these expansions. In any case, what we have on this last line right here, I'm going to explain this a little bit more. Let's look at this last line right here. I had to write it on two separate lines. No, all right, let me get rid of some of this. Let's look at the very last two lines. All right, so what we want to look at is this one first. So assuming that this thing right here can reduce to this one, this is xi. And I'll go through a calculation to make this a little bit more clear. And then this will be times this thing right here, this horrible thing. But all that matters, and this is something right here, this thing right here, this horrible thing is something in TDH star right here. So in other words, we have xi times, on this very last line, xi times something in TDH star. So in any case, this thing right here, it lies in this. So that completes the proof. All right, let me open up Paint so I can give you show you a calculation, because this is kind of confusing. This is like the last thing I had. I thought this was going to actually be a problem, but it's beautiful that this actually works out. It's amazing. Like I said, this construction is so carefully put together. Let me clear these drawings. So now let me open up. All right, so let me put this to the side. I have a calculation on my whiteboard I'm going to read off. So, all right, so let me see. All right, give me a second. All right, so, well, let me kind of just remind you of the setup. So we have t, so what we have is x is equal to lambda d 1, 1, 1, and then g, where g is not in H, and then lambda d. And then we have xi is equal to lambda d uh, 1, 1, comma 1 yi. And just to remind you, where do the g's and these yi's come from? They come from this fact, right? The fact that we have this right coset covering condition right here. All right, so they come from this. And here's the claim. The whole, like, the main part of this lemma is that we are claiming that we have that this right coset is covered by these left cosets. So what we did is we said, all right, well, let's consider this thing right here. Gn minus 1 to h and u, and this is going to be in here, and then we have that, let's see, we have that hg is equal to yi h prime. And then what we want to do is we want to show that this product right here let's see, lives inside of I think we want to say xi, this right here, yeah, this left coset, and that will prove it. So all right, so let's just and the point, let me also pull up the document again, because what was the confusing part? I want to explain these deltas and stuff. The confusing part were this block right here, this block right here, and then it's like, where all these deltas come from, where all these epsilon come from, why do we have a block of yi's here and then a yi in the end? I want to just do a really baby calculation to just, I had to do this once I did this baby calculation, I was like, oh, okay, this is obviously true. So let's just take t, or let's do d equals 3. So 3-ary case for shits and giggles instead of just the binary case. And then we're going to take t equal to u, and we're going to be equal to this. We want this thing right here. So this is, so it's like you take the fundamental d-ary caret and then you glue on this. And we want it glued on the last leaf because that's really the problem. The problem is the reason why we got all these blocks of g's and yi's and then have to introduce the epsilons and the deltas is because at some point in building up the caret, you have to glue a caret at the last leaf. That's the problem. So let's figure out what happens here. So what we're gonna have is this right. So let's work out this product and see why we need to do what we did in the proof. So we had 1, G2. Let me look at my board. Oh, so this is G2, G3, G4, and then H, and then just this, and then times the fundamental caret 1, 1, and then G fundamental caret. All right, so now let's expand this triple. So just copying down the first thing, and now we're going to expand this triple. So we have to clone the last spot. So it's 1, 1, and now we take this G and replace it by G, G, G. So now here's our block, right, of G's. In this case, it's really short because we only had to do one cloning. Like if we had something like this, 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 you would have more, the block would be longer. It'd have it would be 4 G's, I think. But anyways, this is just a baby calculation to just show what's going on. So now these trees are the same, so we cancel them out. And then we get 1, G2, G, so now, okay, sorry, be a little careful. So we have G2 times this 1, so we just get G2. So this is like epsilon 2, but epsilon 2 in this, yeah, so what we have here is epsilon 2, but now all we need in this case for epsilon 2 is just the identity element. And then we have G3, G, G4, G, and then G, and then, whoops, this is a little sloppy. So what we have here is like epsilon 2 is equal to 1, epsilon 3 is equal to G, and then epsilon 3 4 is equal to G. So that's why we have to introduce those epsilons, because maybe you have this block because you cloned at the last coordinate, and then so you have to throw in these epsilons here. They're kind of like just, yeah, I mean, the epsilons really don't matter a whole lot. All that matters is that there is no there is that you have this G. The very last G is by itself. That's all that matters. And actually, no, not just by itself. Sorry, but it's not. It's HG. Sorry, I did this calculation. Oops. Why is that like that? So it's going to be HG. All right. So now HG is equal to YI H prime. So it's G3G, G4G, and then this is going to be YI H prime. Now I want to split this off. So the thing you might want to, so here's the natural thing, and this is what I did, and then I ran into a trouble. I was like, oh, just split it off like this. Oh, sorry. Let me actually write all of them in. So it's got, I think it's 1, 2, 3, 4. Okay, so it's 1, 2, 3, 4, and then YI. And then split it off like this. And you get 1, G, 2, G3, G, G4, G, H, and then the tree. I won't write it because I don't have room. And you're like, okay, well now this, I want to show that this equals reduce. I want to show that this reduces to this. Let me make sure I got this right. But this is definitely not true. Why? If these were equal, the only way these could be equal is that this is not true. This thing right here does not equal this thing. Because what happens to get equality, you would need to add a caret here, right? To get true equality. If you did that though, you're cloning the last spot, so you have 3 y's, but look at, you have nothing there. So what you need to do, this is the trick. You don't do this. This is the mistake I made. Don't do this. What you want to do is you want to throw in a yi here. And then if you do that though, here, you need to put in, well, this should actually be yi inverse G3, G, and then this right here should be yi inverse G3, G. Okay, replace that. And then this is what I just said was delta. These were the deltas. So if you clone at the last spot, you need to like split off these yi's, because then this thing right here won't actually equal xi. You need to split off some yi's, but then in order to compensate for that, you have to throw the yi inverses over here. That is, you need to throw those deltas in. So depending on whether or not you need to throw those in, and then depending on whether or not you add a caret at the last leaf in the process of building the trees up. And then of course this right here, this thing right here, now this definitely, if you remove this tree right here, that's gonna be, when you remove that, you'll also remove this block and replace it with just 1 yi. So this definitely just reduces to lambda 3, 1, 1 yi, lambda 3 times, this other thing right here that I don't care to write out. I'll just write 3 lines, this thing right here. And so then this is, well, maybe I'll write it on this line, very last line. Whoops. This is going to be x I times this, and then in the final form, it's going to look like delta 2 G2 epsilon 2 delta 3 G3 epsilon 3, oops, and then delta 4 G4 epsilon 4. Sorry, I'm a little distracted. There's a million dogs barking. You probably can't hear them. You never hear them in the recording. I don't, when I was recording my class during the summer, the dogs would be barking all the time. And it just felt like they were literally in the office here with me. But they weren't. And I'd always apologize. And then I'd listen to the recording over and like you can't even hear the dogs barking anyways. So this is delta 4, G4, epsilon 4. And then the last thing, this is actually H prime right here, is H prime times this. And then this whole horrible thing is in this. So we are in that left coset. So we did it. We proved it. So let me go back so you can see what's going on here. So that's the reason for introducing this block of yi's right here. And then these blocks of, then having to throw in these deltas along with the epsilons. But all that matters is that you have, when you split it off so that you get this thing right here, you get that times this thing right here. And that's the same thing as xi, whoops, times this element, which belongs to TD H star because H prime belongs to H. So this thing does definitely hold right here. Yeah, now that I'm like actually going through the details, like speaking them, like verbalizing the results and the details, it's like this is so damn clever. I'm really proud of this. I didn't think this paper could get any better, but this makes the paper way better even now. These calculations, this is really brilliant. All right, so now we got the three lemmas out of the way. So let's just remind you what it says is that it says that if this right here does not satisfy the coset government property, then the Thompsonification doesn't either. That is, if the one inclusion doesn't satisfy the WAP, then the other inclusion doesn't satisfy the WAP. And that's going to be important here now. So let's work through this. This is the construction right here, actually. All right, so again, how does this help us? How does everything I just show help us get an infinite index inclusion of two unfactors, which is singular, but doesn't satisfy the WAP? Well, now my goal is to generalize this considerably where we can construct such an inclusion of factors from any group. And I think that's possible using free products. So naturally, the first example I went to was the infinite dihedral group because that's like the easiest free product you can construct. And I don't use the fact that this is, I don't know, I'm not really using this fact that it's the dihedral group a whole lot. Not really. Basically what I'm using is like the fact, sort of using the fact that this group is really of the form G free product Z2. And so what I want to do, how I want to generalize this is by Thompsonifying maybe like this inclusion. And then I claim, I don't know, something like this, I can prove that if you take this, so this would be like your GH and this would be your G here, then when you do that and you know, Thompsonify it, I guess, I don't know, whatever, I'll just leave that blank. Then this will be singular but doesn't satisfy the WAP. So I need this. Well, first of all, this is gonna just the normalizer of G inside this free product is gonna be trivial. It's just a general fact about free products. Would be cool if I could show that this is not always irreducible. I mean, I haven't even gone through the actual construction. I'm going to like try to generalize this already. Anyways, but I need to show that this doesn't satisfy the WAP, the coset government property. I don't know. So I'm thinking maybe like if we do this with free product in a clever way, or maybe the amalgamated free product, it will work. I don't know. Anyways, let's work through the dihedral group, and maybe it'll be clear how to generalize all this nonsense. So we're going to consider the infinite dihedral group which is this free product right here. So this is not ICC, which is cool. It's going to be a really nice fact. And in fact, for free products, we have this really general cool fact, this following cool dichotomy, that any free product non-trivial groups is either ICC or just isomorphic to D infinity. Um, so this is kind of cool. We're not really going to use it though. You can actually just like you can like explicitly determine all the conjugacy classes. I think every one of them is finite, if I'm not mistaken. So it's very far from being ICC. And we also have this other nice fact, standard fact about free products. So if you have that these are groups A and B, then the normalizer of A in the free product is trivial, as it's self-normalizing, and then the same goes for B. All right, so why does this give us, if I can, I claim that this inclusion right here is the conclusion we want. Oh, that should be a B. But why does this give us an infinite index conclusion of 2 n factors, which is singular but doesn't satisfy the why? Well, note for any n, these elements right here, and in fact, A, B generates a copy of the integers, if I'm not mistaken. All these elements give rise to distinct left cosets of this cyclic group in D infinity. So that means that this index is infinite. So we got infinite index. Good. That's good. We're going to get infinite index. Now, because this thing is not ICC, there cannot be any subgroup such that this thing is irreducible. So this is not super important, but it's kind of cool that we're going to start with an inclusion that's not irreducible, but when we consentify it, it's going to become irreducible. But the fact that this is irreducible is just already obvious in this case. This is a finite group. There's no way it can be irreducible. Yeah, there's just not, it's not the case that that every non-trivial element of this can have infinitely many A conjugates. So this says that this is certainly not irreducible. Oh, I didn't mean to say trivial, but not irreducible. However, when we Thompsonify it, we're gonna get irreducibility. So what we're gonna do is we're gonna take H to be this cyclic group, G to be this guy, and we're gonna Thompsonify this inclusion. And when we do that, we're gonna get this right here. Now, the reason why, so what this says is that because this d-ary cloning system on is this diverse, it's always diverse. Every non-trivial element is going to have infinitely many FD conjugates. In particular, that means every non-trivial element of this has infinitely many TGH star conjugates. So by Smith and Wiggins' characterization of irreducibility, that means that this inclusion right here is irreducible. So hence these are two n factors. So using basically this lemma up here, I can't scroll up, but using the index calculation, we get infinite index because this right here is infinite index inclusion of this groups. So the inclusion of the von Neumann algebras is infinite index. And then we also get that these are 2 n factors because in fact, this inclusion right here is irreducible. And that's going to be super important because that's going to allow us to compute the von Neumann algebra normalizer using Smith and Wiggins resolve again. So they have this, maybe I'll scroll up to it actually. So let me see, where is it? Oh, it's right here. This is a really nice result by Smith, Wiggins, and Stuart Roy, I think actually. So you have this inclusion of groups, countable groups, and then you assume that this is irreducible, which we have, which is awesome. Then it turns out that the von Neumann algebra normalizer is, sorry, it's going to be U times lambda G, where U is a unitary in L of H and G is a normalizing element. And then, of course, is the usual group theoretic normalizer. And what this states roughly is that the von Neumann algebra normalizers are made up of normalized, in the irreducible case at least, of made up of normalizing group elements modulo a unitary from L of H. So what that says is that if you know that this group normalizer is trivial, which we do, so we're dealing with a free product, then this normalizer right here is trivial. the von Neumann algebra normalizer is trivial. It's just going to be it's just going to be equal to u of h, and so it's going to the von Neumann algebra it's going to generate is just going to be L of h. So, i.e., it's singular. The inclusion is singular. That's what. All right. Oh yeah. Where is it? Yeah. If the normalizer generates, if you have an inclusion of n and m, and the normalizer generates n, then it's said to be singular. So that's what we have. So let me go down to this example, back to the dihedral group. Um, so what do we have? So we have that this oh yeah, this is not so we have this inclusion right here. This implies that this inclusion is going to be irreducible right here. And then yeah, because every element of TDG star has infinitely many FD conjugates. So in particular, that means every non-trivial element of TDG star has infinitely many TGH star conjugates. And so by Smith and Wiggins characterization of irreducibility, this is irreducible, and they're both 2-1 factors. And then this is the fact about free products, because the normalizer of A and D infinity is trivial. The above lemma tells us that this translates to this normalizer being trivial. So this together with irreducibility inclusion of the von Neumann algebras allows us to conclude that the normalizer of this guy in here is trivial by Smith and Wiggins result. Now, finally, this is the important part. This thing is because this is supposed to be A infinity inside of D. Sorry, this is supposed to be right here, A inside of D infinity. This doesn't satisfy the coset covering property. It's like this follows from the fact that it's not irreducible, because WAP implies irreducible, so it can't be satisfy the WAP. But you can also just like exhibit a specific set of elements to show that the coset covering property is not satisfied. By the above lemma, this translates to this not satisfying the coset property either. And then that means that this inclusion does not satisfy the weak asymptotic homomorphism property. So putting all this together, we have that this is an infinite index. I didn't put in, it should be an infinite index irreducible inclusion of 2-1 factors, which is singular, but does not satisfy the WAP. And also these are McDuff factors. So this is really, I think this is really cool. So this gets us an example, but as I said earlier, I think we can generalize this to get a sort of machine which takes in any group and spits out an inclusion of von Neumann algebras, which is singular, but does not satisfy the WAP. And I think you're going to do that using maybe some careful construction with free products, or maybe amalgamated free products. So maybe that's just like not even, has nothing to do with cloning systems. So here's a question, maybe. Let me try to phrase a question for you, because it doesn't even have to do with cloning systems. It's just like a fun group theory problem to think about. Given so, and this would be like this would be awesome, because this would be like a machine similar to our McDuff factor machine, where you plug in any group and you get a McDuff factor. This would be a similar machine where you can plug in any group into this Thompson machine and get an inclusion of von Neumann algebras which is singular but doesn't satisfy the WAP. So here's the question: given G, does this is all we need to know. If we can answer this, or some answer like this, we have our machine. Does G inside here, say Z2 or maybe anything, satisfy coset covering property? Or let's say, does blah not satisfy? Maybe it does in some, I don't know. In some cases it does, or maybe it doesn't for some nice class of groups G. But it'd be cool if we don't have to have any restrictions on G. Or maybe we need to do like G inside G alpha Z2 or amalgamated product. Amalgamation. Or maybe not even Z2 anymore, but like z some amalgamation with some fixed H, which works. Um, this at least gives us one example, but I think that what would make this really interesting is if we can like get this machine which produces all these inclusions from a given inclusion. Um, so maybe if you maybe there's a way of doing that. I'll keep thinking about it. Of course I'm going to clean all this up, this all this section up, and of course I'm going to clean up the whole paper, and then I'll send it to you, or I'll send it to you now. But I'll let you know when I've got this section and the entire paper cleaned up. But this is something to like think about. Maybe you can think about. Maybe you know, or we can work together on this because this would give us, like as I said, a cool machine that's similar to our McDuff factor machine. All right, that's all for now. That was a lot. That's probably way longer than I expected, but I think this is a good video. Interesting, a very interesting result. Yeah, very careful, very careful construction, subtle and a lot of it's very delicate construction. All right, anyways, that's all I got. So I'll talk to you later, I guess.